Okay, we'll go ahead and get started then. I hope everybody can see the slides and hear me clearly.
Yep.
Okay, so hello everybody. My name is Utkarsh Krishna, and I'm the Vice Chair of the Santa Clara Valley Chapter of the Microwave Theory and Technique Society, that's MTT-SCV. And I would like to welcome you all to our May technical presentation. So this talk will be a joint presentation between the Santa Clara Valley chapters of both MTTS, that's Microwave Theory and Technique Society, and the Antennas and Propagation Society, that's APS. So just a few notes before we get started. This meeting is being recorded, and the links to both the recorded video and slides will be made available to all registrants. A request to all our attendees, please keep your cameras off and microphones muted to help with any bandwidth issues and background noise, because we'll be having a pretty full house. We expect more than 100 people to attend. As for questions, please post your questions addressed to everyone in the chat window. One of our officers will monitor the chat window, and we'll be, during the presentation, we'll take periodic breaks to present those questions to our speaker. Please support us by becoming a member. The links for joining IEEE and MTTS are posted here. We desperately need your support so that we can keep bringing you talks like the one that you'll be attending today. And to follow MTT-SCV events in the future, if you're on LinkedIn, please follow the hashtag MTT-SCV. Once again, that's hashtag MTT-SCV. So to present the rest of the agenda and the rest of the talk, I would like to welcome the chairman of our chapter, Mr. Jay Banwaite. Jay?
So I'd like to welcome everyone to this presentation. As Utkarsh mentioned, this is a joint presentation with the Antenna Propagation Society. I'll just go through the membership slide, the joint presentation. We'll briefly go over the different offices, and then we'll delve into the technical presentation. Next. So we typically have our technical meetings in person at a local facility here in Santa Clara Valley, but as there's a global COVID-19 pandemic, we've gone online, and interestingly enough, we're getting a lot of support from our international community. So welcome to folks from around the globe. Thank you. Next. So the APS chapter offices, the chair for the Antenna Propagation Society is David Norlander. I believe he's online. Vice chair is Paul Zander, and the treasurer is Hawkins. So for the local Santa Clara Valley MTTS, I'm the chair, Jay Banwaite, and the vice chair who was talking earlier is Utkarsh Unikrishna. Our secretary is Tan Tui, and our treasurer is Tom McKay. As Utkarsh mentioned, we are a volunteer organization, and part of that requires new volunteers as we go through each year. So there will be an email to our MTT membership, Santa Clara Valley membership, for new volunteers. So if you're interested, when you get that email, that'll be sent out from our nomination chair, Dr. Paul Cunner. You can reply, and we can get you on the ballot. With that, I'd like to transfer to our treasurer, Tom McKay, who will introduce our speaker and details on our technical presentation for today. Tom?
Thank you, Jay. Yes, my name is Tom McKay. I'm the treasurer of the Santa Clara Valley MTT chapter, and it's really my privilege to introduce Jeff Shamblin. I met Jeff in 2008 when he was CTO and chief scientist at Ethertronics, And I can tell you, having visited the facility there, that Jeff is the real deal when it comes to multi-band, actively tuned antennas. You know, having the right mixture, I think, of knowledge and experience and hands-on know-how make Jeff really, I think, one of the heroes of physical implementation of MIMO systems that, you know, some of our community thought, you know, 10, 15 years ago would not be possible, but these have been brought to life. And I, you know, would like to just say that it is my privilege to introduce Jeff, and I think we're going to, although he's focused lately on some millimeter wave topics, we've asked him to kind of look at the sub 6 gigahertz, probably moving now to sub 8 gigahertz with Wi-Fi 6 being interesting, and I think there's a lot of value, and I'm sure you're going to learn a lot. So thank you all for attending, and Jeff, thank you for presenting to us today.
Okay, well, yeah, thank you, Tom, for the introduction, the kind words, and yeah, I want to really thank you know, Tom for inviting me, and also the local IEEE chapter up there in Santa Clara for inviting me and allowing me to give a presentation. I will go ahead and dive into it, and I think, as they had mentioned, we will periodically. I'll stop and see if there's questions. Let's see. Okay. So I'll go ahead and share my screen. Can you see my screen?
Yep.
Yes.
Okay, so here goes. The presentation, I mean, yeah, just a bit more of my background. I've been an antenna engineer my whole career, so I tend to look at, you know, really, I think what most people are working on nowadays, you know, commercial communication systems. I look at it from the antenna perspective, but I wanted to put together a set of slides that kind of not only talk about, you know, how you'd integrate an antenna, but also keeping in mind that, you know, the antenna is going to sit and either, you know, provide benefit or hamper that overall RF system or the communication system. What I'll be talking about tonight is going to be kind of focusing on a client-side device. And what that means is instead of, you know, talking about base station or node type antenna systems and RF systems, we're talking about the device that, you know, there's quite a bit of work going on, a smartphone, a smart watch, M2M IoT devices, vehicle tracking units, medical devices. In other words, really where there has been and there currently are quite a few challenges on the communication, the RF system, and the antenna side to really design, you know, multiple radios in a confined volume and get the whole thing to work or play well. I'll briefly kind of highlight some challenges related to getting antennas designed into these small volumetric areas or volumes. I'll touch a little bit on active antennas. As Tom mentioned, I spent quite a bit of time, probably 12 to 15 years working with active and tunable antenna technologies that could be brought into, you know, cost effectively into, you know, commercial client type devices. And also I do want to touch upon beam steering, because that really is very relevant today as the industry transitions from 4G to 5G. As we bring 5G on, really from the value added from the antenna system side is going to be from not driving a single antenna, but now going to higher orders of MIMO, and to introduce or continue to implement, you know, beam steering in either a massive MIMO array or as a phased array. So starting off, I just want to very quickly just kind of set the landscape for really what we have to deal with in terms of frequency bands and antenna size constraints. Everyone hopefully should be pretty well aware, as the industry has gone from 2G, 3G, 4G, and now we're, you know, kind of staring at 5G. We continue to add more frequency bands. Recently, the last couple of years, the 600 megahertz spectrum has come online through T-Mobile here in the U.S. 3.5 gigahertz band is becoming more popular. As Tom pointed out, Wi-Fi, which typically used to be more of a 5.15 to 5.8 gigahertz band, is creeping up at or above 7 gigahertz. So as a function of time, we keep having to address more frequency bands, and where it really impacts the antenna design and then flows back down into the RF system design of a client device, that smartphone or IoT device or a medical wearable device, it kind of flows back down into having to integrate antennas that have to cover lower frequencies and or wider bandwidths. And I should be able to hit a few slides that will kind of bound really what's feasible or possible as we integrate an antenna into a device. Don't want to get too heavy into equations or calculations, but this actually, Wheeler's formula, I've given this presentation many times over the years, and it's very, it's relevant and a pretty simple calculation. And what it does really, it captures or tries to capture that basic question. If you're developing a client device, a commercial device, a wearable, handheld type mobile radio system, and it has to operate at a set frequency F, and you want to occupy a certain bandwidth, and keeping in mind the more bandwidth you get, the higher data rates you can support. The Wheeler's formula helps to set an upper limit on what bandwidth you should be able to efficiently achieve at a frequency. And it really talks not about a physical volume, but an antenna mode volume. But nonetheless, what this equation does allow us to start to really, again, relate a set frequency, a bandwidth, and then translate that to an antenna mode volume, and then ideally a physical volume. And it really helps device project teams start to size a device for a specific application. And to kind of simplify it a bit, I took that and I plotted it on a graph, and this simple XY graph really is mapping the frequency on the x-axis. That would be the center frequency that you're operating at. That could be an LTE band, band 13, band 17, band 8. And the curve I've plotted is a fixed 140 megahertz bandwidth that we are attempting to achieve. And if you plug that into Wheeler's formula as you're driving the frequency of operation down, as you can see, and as you would expect, the antenna mode volume grows, and it grows quite rapidly as we drop below 1 gigahertz. And that's the way things are, and it's a function of, as you decrease frequency, the wavelength increases, the antenna wants or needs to be a larger structure. That being said, if you think about what's happening with everyone with a smartphone or a smartwatch or maybe a small radio system that's being used for a metering application, we can very quickly see if someone is going to attempt to implement band 13 or band 17 or maybe band 8 in a LTE band in a device. All of a sudden you can start to see when you're going to start running into problems. And the problem will be you're going to have difficulty achieving the bandwidth that you want for efficient operation if the volume you're attempting to design and place the antenna or multiple antennas in is not sufficiently large. So again, we can look at Wheeler's formula to kind of set an upper limit, or to start to bound the problem of how big of a device do I need, or will I be expecting an inefficient antenna system as I integrate that into a device. And you can actually, as I said, I have currently worked at Taoglas, and I've worked at other antenna companies previously, and it's a common problem among antenna companies that develop ideally a standard product like a cellular 4G antenna that can be procured and then designed into a product. The problem is, as you try and drive that LTE antenna below 1 gigahertz to service the LTE bands, if the ground plane is not large enough, you get reduced, in fact, you can see it in measured data, you'll get reduced efficiency and reduced bandwidth. And that's really an example of Wheeler's formula in action. And it's typically what we're showing here is a demonstration board and an antenna. You can buy this on DigiKey, and other antenna companies have it. It's kind of a common tool for developers to get a hold of an antenna and start to see if it's going to fit their application. but this is a common cut down test, and the idea is to educate a customer. As I start to reduce the length of the ground plane that the antenna is on, I'm not changing the antenna volume, but I am changing the ground plane that the antenna is driven on. And by the way, that ground plane is going to be the PCB, the multi-layer PCB of the radio system you're designing for this client device. As you reduce the ground plane at the lower frequencies, you can see the bandwidth decrease and the efficiency drop. And again, what's happening is the antenna really at lower frequencies, the volume, physical volume that the antenna occupies is not large enough. That antenna, the antenna mode volume is actually encompassing the entire antenna and ground plane structure. So that really leads to the next slide, and this is again kind of a set of slides that have been used, being used now and have been used in the past to help educate. Really, it's not to educate antenna engineers, but to educate really RF system designers. Like I think a lot of the people on this phone call are. You're doing some RF system work. You're developing a say a radio system that's going to sit into a modest volumetric platform. When you place an antenna inside of it, not only do we need a volume or area for that, a landing pad for the antenna to fit, but we need to have a keep out area. In other words, the fact that the antenna, unlike a connector or a passive component, the antenna is going to radiate. So it's going to have EM field structures, you know, emanating or radiating from the antenna element. And there's a certain minimum volume, and we can relate that to a minimum area needed to allow the antenna to be positioned in a device and operate efficiently. We call it the keep out area, and it can be frustrating because there's always antenna companies trying to, you know, better each other. So there's always that search for the world's smallest antenna to make everyone's problem easier. The problem is there's really no value in the world's smallest antenna if it has a large keep out area. So it's not so important really what's the size of the antenna that's going to be integrated into a device, but what's more important is what is the size of the keep out area or the keep out volume needed for that antenna to be integrated in and efficiently operate and provide, operate over the bandwidth that we're really targeting. This is just a slide here, which is really helps to, you know, moving from an equation to a bit more of a visual to help people grasp the concept. This is a 3D EM simulation, and really what's happening is we're simulating an antenna that is driven off of a ground plane. Again, that ground plane could be a multi-layer PCB of a radio system that's being designed for a device. And what we're looking at on the left is at 800 megahertz. You can see the antenna, the electric field strength mapping at the antenna and down the ground plane. And then on the right, we're looking at 1800 megahertz. We choose 800 and 1800 because 800 would tend to represent what we call LTE low band, 600, 700, 800 megahertz operation. 1800 is kind of sitting in that prime LTE mid band, 1710 to 2300, 1710 to 2700, depending on how you want to define it. But at these two different frequencies, you can see at the higher frequency, at 1.8 gigahertz, there is much less electric field strength being displayed or induced on that ground plane. So the antenna, this is a good visual to show that the antenna mode volume is actually shrinking as you go up in frequency. You don't need as much of that ground plane as you would if you try and drive at a lower frequency. Any questions so far? Okay, and this is kind of a newer slide I put in once again just to help to even simplify it more, really break down that design or integration process of an antenna in when you're looking at designing one or multiple antennas or integrating them into that client device of finite volume. Think about the antenna in terms of a wavelength. And really what that means is if you think about the most common antenna would be a half wavelength dipole. Well, that's a half wavelength and extent. A resonant monopole is typically a quarter wavelength wire element above a ground plane. So we're looking for a quarter wavelength type dimensioning to get that efficient monopole type structure. Another good data point is kind of a classic example that's done in a lot of research papers in the past and a lot of simulations. Typically people will sit and map isolation between pairs of dipoles. And if you take two resonant dipoles, you can maintain 20 dB of isolation between collinear dipoles, but you need a half wavelength spacing. So we can start to look at the frequency of operation. We quickly know its wavelength, and then from its wavelength we can start to determine as we start looking at a radio system that needs to fit into a certain volumetric if we're going to have bandwidth or efficiency problems. So the plot on this chart's a very simple plot where I'm just mapping frequency and wavelength, and what I'm mapping is the green line is one wavelength and the red line is a quarter wavelength. Interestingly enough, or unfortunately, difficultly enough, what is happening is, if you think about smartwatches or very small IoT type devices or medical wearable devices, at a lot of the frequency ranges we want to use, that entire device is coming in at less than 8 centimeters. So it's, as you can see, depending on the frequencies we might need to design an antenna for a radio system, we're going to have problems getting either the efficiency or bandwidth because the device size will not support a large, electrically large enough antenna. So again, you just kind of that concept, think about an antenna in terms of wavelengths when kind of doing some product or radio system planning. Here's an interesting curve. Again, you know, as we interface with customers that are developing client type products, they'll typically integrate a cellular radio or a Wi-Fi radio. They'll also quite often have GPS functionality in that device. And if it is again a small volumetric device, smartphone size or less, typically what's going to happen is because a GPS antenna is a very narrow bandwidth function, and the main GPS frequency is 1575, for example, the frequency is high enough, the bandwidth is definitely narrow enough, we can go in and even in a small device match the antenna. So you'll typically see a 10 to 15, 10 to 17 dB return loss on a GPS antenna integrated into a commercial consumer device. Now, on the other side of the coin, when we need to integrate a cellular antenna, say for 4G, the problem is we might need to cover as low as 700 megahertz. We'll also need to pick up some mid and high band frequencies, 1800, 2700 megahertz. So because we're trying to grab a lot of bandwidth in a confined volume, the volumetric or the volume of the device being designed may not be large enough to support a better match. Typically what you're going to see is only a 6 to 10 dB return loss for that integrated cellular antenna in a device. And that definitely holds true for everyone's smartphone that they're holding. I'd be highly surprised if you're getting better than an 8 or 10 dB return loss across the majority of the frequency bands. It's just, unfortunately, if you look at the thin form factor and the minimal volume that is allowed for the antenna systems and smartphones, very difficult to achieve good return loss, or i.e. a good impedance match over the frequencies needed. And the problem is that cellular frequencies, when it's time, if you look at kind of the little summary sentence there at the bottom of the slide, that moderate return loss for a cellular antenna could lead to radiated spurious emission problems when you get to certification testing. Quite often, if there's a RSE failure during certification testing, quite often it can be traced back to a moderate to poor antenna return loss and reflecting power back into the PA. So here's a slide that again kind of points to, it's kind of the good news in terms of integrating a cellular antenna into a small volumetric device. The question is, how good of a match do you need, assuming you're not concerned with RSE or some other issues? If you're just looking at efficient antenna operation, if you map mismatch loss as a function of return loss, once you get an 8 to 10 dB return loss, you're at a point of diminished return if you're just looking at trying to drive up or gain additional efficiency out of the antenna. And that's just a function of the kind of the equation driving that mismatch loss calculation. So, not to be sloppy, but once you get an 8 to 10 dB return loss, as long as you're going to pass RSC, radiated spurious emissions type testing, there's really, a negligible benefit for getting a better match. And if you need to implement a matching circuit, say a passive matching circuit with L's and C's, if you've already got an 8 to 10 dB return loss, you're probably going to bring in an equivalent amount of loss in your matching circuit than you would gain in efficiency by getting a better match. So it is really kind of truly, in terms of better efficiency, that 8 to 10 dB return loss definitely puts you at a point of diminished benefit. Before moving out of the antenna topic, just one real quick discussion, and this definitely applies to cellular antennas integrated into client devices. What we see is it's very hard to maintain a high directivity antenna in a small device because the antenna cannot be designed electrically large enough. And as it turns out, we don't want it anyway because most consumer commercial type radio systems are mobile systems, that smartphone, the watch, medical wearable devices, even a lot of the IoT type devices. So since you don't know the location or orientation of your device, you really can't predetermine what type of a radiation pattern you want anyway. So typically we design for low directivity, 1 to 2 dBi peak gain from an antenna system integrated into the device to provide very wide beamwidth coverage. And since we do that, it's really what we want to stress is it's not so important to design the antenna that's going to be integrated in for radiation pattern type or shape. What's more important is to try and drive the efficiency of the antenna up. And that really holds true for the, today's modern cellular network and the client devices that are on that network. So again, looking at kind of a typical antenna you would find for procurement to design into a product, this is a 4G ceramic form factor LTE antenna. Again, we tend to stress efficiency, not so much radiation pattern shape, because radiation pattern shape really doesn't matter at most of the frequencies because we can't really design a directive antenna anyway because we don't have enough electrical extent in that small volumetric device.
Oh, so Jeff?
Yep.
Yeah, Jeff, this is Tom. I have, there's a couple of questions. One question is there any technology which can integrate Bluetooth, Wi-Fi, and cell network, replacing all three of those in one go?
In a single antenna?
Yeah, I think that's the question.
Well, again, and that's where actually I think you'd probably get a more relevant answer from the people on this call. From an antenna perspective, we could design a single wideband antenna that would allow you to cover the frequency ranges you pointed out, GPS, Wi-Fi, the cellular bands. One of the problems is from that single antenna, if it winds up having a single feed port, you need to do the filtering out to the different radios. And as soon as you do that, either diplex out to the different radio systems, you start to incur losses for one. So there are some problems with trying to replace a handful of antennas with one.
Right. I think the question was about Bluetooth. I may have misspoken. Yeah, GPS. But anyway, I think that answers the question. One of the other questions is, if directivity is less, how do you guarantee good signal reception?
Good question. One way of looking at it is, as soon as you define the problem as I have to design a device that's going to be a client device in a cellular network, and it's going to be mobile. You don't know the orientation of that device, and the orientation is going to change. Then what you need ideally is an omnidirectional coverage from that antenna. An omnidirectional antenna would have 0 dBi directivity. So the directivity from an ideal omnidirectional antenna is 0 dBi. The gain would be the directivity minus losses. So if you had a pretty well-designed antenna that had 1.5 dB of loss, you would wind up with an omnidirectional antenna with a gain of minus 1.5 dBi. And then you would use that gain in a link calculation to verify that the cellular system and that client device will make the connection and support the bandwidth you need. Yeah.
I'm sorry, I missed that. You say, where'd you get the minus 1.5 dB?
Well, I'm just saying, because if the design goal is to design an antenna in a client device that is going to be in a cellular network and it's going to be mobile. You don't know the orientation of the device and the orientation is changing. What you need to do is design, ideally, an omnidirectional antenna, one that radiates equally in all directions to handle that mobility part of the problem. As soon as you just say you want 0 dBi directivity, or you want an omnidirectional antenna, that is 0 dBi directivity. Now, directivity is, you need to apply a loss factor or multiply efficiency to directivity, come up with the actual gain of the antenna.
Okay.
So no antenna is going to be, yeah, so even if you design a great antenna and you've only got 1.5 dB of conductor losses, mismatch losses, coupling losses, you'll have minus 1.5 dBi omnidirectional antenna if you could design that omni antenna.
So
and that is what you lose in a link. Yeah, go ahead.
So I know there's actually a couple more questions, and I had one. You know, I see that you're getting more electrical length with ceramics on the sort of radiating element, but on the ground plane, it seems like we're stuck with you know, a huge size. But are there dielectric loading methods or something like that could address the ground plane side of the problem?
Not that I've seen, and the main problem with dielectric loading of an antenna or even a ground plane or other regions around the antenna is you need to make sure the dielectric is going to have a very low loss tangent, a low loss material, and then it tends to reduce the bandwidth. So as you go from a well-sized antenna to a smaller ceramic-based antenna, typically you see the bandwidth shrink. The efficiency tends to stay high, but it really forces them to ceramic materials with very low loss tangents.
So maybe this question here applies. Is it related? And there's another after this one. What are the challenges in current phone designs, like the glass body and other things like that that come into play? So maybe the materials, industrial design or consumer design aspects. How do those? What are the current challenges there?
Well, yeah, I mean, there's a lot of challenges. What has always been a challenge since LTE came along was the need to integrate two antennas in that small volumetric. Another challenge, which was hitting, 2008, 9, 10, and has kind of stabilized, is the smartphone became extremely thin, again, putting stress on the antenna. So it's very difficult to get any antenna height above a ground plane. We're always looking for separation between an antenna and ground plane to provide more efficient propagation or radiation. So that is typically a problem. And the inability of getting the antenna away from a battery. Again, it is so crowded in a smartphone. There's maybe not enough separation between the main or secondary antenna and that battery. There's not enough height because it's a thin or slim smartphone. Yeah, quite a few problems.
So I think we're gonna we maybe could hold a couple questions that have come in for the next break. I think it's possible that you're going to address at least one of the questions on 5G in your next section. So I have a couple more questions, and we'll probably get a few more for the next break. So I think it'd be good to.
Should I continue on?
Yeah, I think we should continue on right now, and then we'll come back. We'll select a few more questions, and then at the next break.
Okay.
The next logical break. Yeah.
Yep. So here it goes. I mean, we've talked about the frequencies we need to service in a typical device and kind of the difficulties of fitting one or multiple antennas in a small volumetric. So over the years, companies have researched and actually implemented the active antenna tuning techniques to help a small antenna or an electrically small antenna perform better in a small device. And when we talk about an active antenna, really what that means is you can break it up into three regions. The most common that I think people are familiar with would be that open loop active matching or closed loop active matching. In other words, you have an antenna structure, and then typically on a passive antenna, there might be a 2 to 4 component matching circuit. inductors and capacitors, typically chip inductors and chip capacitors, O4, O2, or O2, O1, very small components, say in that smartphone or medical device, matching the antenna over the wide frequency ranges we need. That is a passive antenna, so it's a pretty easy, conceptually, an easy step is to say, hey, let's take the passive antenna with passive matching circuit, pull out one of the fixed capacitors and drop in a tunable capacitor. And it really worked out well, because if you go back 2005, 6 through 2010, 11, look at the companies that were developing tunable capacitors. You know, Cavendish Kinetics, Peregrine, RFMD. A lot of companies developed typically a tunable capacitor that could be used to provide dynamic variation of capacitance, drop it into a matching circuit. Now you've got a tunable antenna. But what you need would be control signals to kind of determine when do I tune the antenna. You know, what am I tuning to? And I'll briefly touch on that. The second main technique is band switching, or an active aperture technique. It has nothing to do with the matching circuit. Assume we have a passive matching circuit or don't need a matching circuit. We just have an antenna structure, a metal element that is you know, dimensioned and shaped to radiate at a certain frequency range. The idea would be to couple an active component. That could be a switch, or it could be a tunable capacitor. Actually couple that tunable component to the radiating element to actually allow for dynamic variation of the frequency response. Not to improve the impedance, but to literally shift the frequency response of the antenna. The third technique is beam steering, and that, as it turns out, provides the most benefit, because if you think about it, you can impedance match an antenna better or shift the frequency, and what we have seen is you can pick up 1, 2, you know, maybe 2.5 dB of total system level performance, but it's really hard to get that 2 or 2.5 dB. But as soon as you step into a beam steering technique, if you get dynamic control of the radiation pattern, all of a sudden you're in that 3 to 10 dB optimization of the antenna, because instead of radiating, as I discussed a few minutes ago, omnidirectionally, because I don't know the orientation of the device, if we can bring some intelligence into that link between a base station and your client device, all of a sudden we implement a beam steering technique, we're picking up 3, 4, 5, 7 dB of improvement. So I'll show some actual examples of a few of these techniques. But at the end of the day, if you look at the blue box on the bottom of the chart, that kind of says, though all antennas are different, basically there are 3 things we can tune. We can tune for impedance, we can tune for frequency response or bandwidth, or we can tune for radiation patterns. First up is the active antenna techniques. Before we get to that, the concept we do want to, and I think I'm talking to a lot of, there's probably some antenna people on this call, but also the RF systems people. What I've seen over the years, and rightfully so, they should be, typically an RF system engineer thinks of an antenna as a device with impedance properties, not so much thinking about the radiation aspects. But the antenna literally needs to do 2 things. It needs to interface with the RF front end, i.e. maintain a frequency response and acceptable impedance properties. But then on the other hand, it needs to really switch gears. It has to have radiation characteristics, polarization, a radiation pattern shape, and the ability to get kind of some efficiency as it radiates. So the antenna really has to do 2 things, but typically what I've noticed over the years, RF system people, and rightfully so, tend to look at an antenna like, well, what is the frequency response and the antenna characteristics? So that's what we have to design the antenna to, but then also we do have to design for radiation patterns, polarization properties, kind of efficiently getting energy through that antenna. But first up on the active antenna technique, and this actually went to production, it was an open loop technique, and really what it is, it was an antenna integrated into a smartphone. A tunable capacitor was placed in a matching circuit, and then there was a lookup table and some control signals. And the idea was some signaling was sent from baseband, a 4G LTE baseband was sending frequency information, and then from a lookup table, just commanding a tunable capacitor to tune the antenna for a certain low band frequency. So that is an open loop technique, and it actually wound up in a smartphone, went into production in 2012. And here's just some slides to kind of highlight, again, a smartphone. And the main idea was that, again, due to the crowded volume in that smartphone, there was not enough room for a well-sized antenna. So the idea was to take a narrow band, low band LTE response and tune it from 824 to 894 or 880 to 960, kind of that flip between bands 5 and 8. And once that was done, it occurred to a design group that, hey, we're able to send frequency information and retune for a lower band frequency response, but also there's proximity sensors and a few other functions in the phone, speakers, microphones. We can actually make predictions as to the use case and actually retune that capacitor to compensate for hand loading or hand and head loading. So that's what was done. So this is an example of an open loop active impedance matching technique that went into production in a commercial device. Going to technique number 2, which is band switching or that active aperture, this was done actually when I was working at Ethertronics. Again, all this information is in the public domain. A lot of this stuff happened quite a while ago. I'm just kind of showing examples of antennas, active antennas that have made it really, succeeded in making it into production, to help provide benefit for that radio system. This is a band switching or active aperture technique, and the idea was, again, there was not enough volume for a well-sized antenna to cover 700 and 800 megahertz. Those lower LTE bands, this is back in 2012, 2013, a typical requirement was we need to cover 698 to 960 and then 1710 to 2700 megahertz. Obviously, the antenna, because we wanted to minimize bezels of laptops, there was not enough volume. Typically height off of the screen, which acted as the ground plane. So instead of a passive antenna, we came up with an active antenna, and what it was the ability to take an antenna structure that had a low band and high band radiating portion from a single antenna structure. We coupled a 4-port switch to the low band portion of that radiating structure, and that allowed us, again, to take information from baseband as to which frequency was going to be used, go to a lookup table, command the 4-port switch. And what the switch was doing was, typically there might be, say, a parasitic element below the antenna element. That parasitic element is floating, and then we connected a switch to one end of the parasitic element. The other end of the parasitic element could access ground either directly, i.e. short the parasitic, or it could apply a capacitive or inductive loading between the parasitic and ground. Designed properly, the antenna, the low band antenna response will shift in frequency depending on what switch setting we applied. So again, it's a pretty complex design process. That being said, once it's done, you just have an antenna structure, a 4-port switch with some passive inductors or capacitors, a lookup table, and a connection back to baseband. Baseband is commanding which frequency band to tune the antenna for. Again, that made it into production, and this just kind of shows really the concept. On the left is measured return loss for 4 tuning states. On the right is measured efficiency. And the concept at the time was we wanted instantaneous high band, 1710 to 2700, but knowing we had a effectively electrically small antenna below 1 gigahertz, we broke it up into 4 narrow band tuning states that allowed us to break up 698 to 960 into 4 different frequency bands. So that's an example of that technique number 2, which is a band switching or active aperture technique. Third up is beam steering, and as I said, implemented correctly, that should provide the most benefit of the 3 active antenna techniques quite often. And the reason for that is, and I hate to say this because I've been an antenna engineer my whole career, but if you think about it, unfortunately, in a cellular-based client device, probably the most inefficient component is the antenna. And the reason I say that is if I have a smartphone and I initiate a phone call, that smartphone is going to connect with a single base station. And when I transmit a signal out of my smartphone, I am blasting my quarter, half, or 0.6 watts over a very wide angular region, not at the intended direction on the other end of the link. So it's a very inefficient process. So instead of having these low directivity antennas, it would make much more sense if it could be implemented to have beam steering antennas that can provide a more directive radiation pattern. And what's kind of important about this slide is it's if you think about where we're at now as we're transitioning from 4G to 5G, at least from an antenna system perspective, that is what 5G is all about. It's going to the antenna system and saying, let's implement higher orders of MIMO to support higher data rates, and let's implement beam steering to provide more directivity and to really boost the SINR of a radio system in a cellular or Wi-Fi type network. So beam steering can be a very powerful tool if it can be implemented. It turns out it can, but it does take some little bit of technology, cost, and some software, things like that. What's interesting is the reason this is kind of the benefit slide. This was a cellular system simulation. Was brought up at a company many years ago, and what we're showing here on the 3 plots on the bottom of the slide is a 7-cell or 7-node cellular network is simulated, and we wind up establishing connections from these 7 nodes or cellular base stations across the different cells. And what we're showing is the area in the mapping of the cells that can support the QPSK, 16 QAM, 64 QAM. The different modulation schemes are dependent on the SINR that can be supported at that location in the cell. So if you take that middle plot on the bottom of this slide and then say, okay, for every client device or smartphone in that network, if I could beam steer and that would provide 3 dB of additional antenna system gain on the client device, you wind up with the modulation mapping on the right. And all of a sudden you see, obviously, the regions of your cellular network that can support 64 QAM and 16 QAM increases. And it's just that direct communication link calculation to prove if you can drive up the antenna gain on either side of that link, you're going to wind up putting more energy on target or across the locations. So that is a justification of, hey, how do we grab 3 dB, ideally 5 or 6 dB on all these client devices? And really the way to do it could be implementing a beam steering technique. This slide here kind of helps to remind us that the modulation scheme is directly dependent on the SINR. Antenna system gain is going to directly influence SINR. So the higher the antenna gain, the higher the SINR, the better the modulation. That's going to be the higher the data rate. And as you move away from a node or cell tower, the signal strength drops, and the modulation scheme that you can support is going to decrease. So again, the benefit being is how do we boost antenna system performance, i.e. gain, on those client devices? I mean, the industry's already been doing beam steering and arrays on the base station and nodes for many years, but the client devices, typically that near omnidirectional broad beam width antenna that's just blasting power in all directions. And an interesting point to point out is within the dense nodes that we find in a lot of urban areas nowadays, it is not weak signals that are the problem, it's interference. So if we can get control of the radiation pattern of an antenna on a client device, increase the directivity, not only do we improve the S, but we also improve the I in the SINR. We can put more energy on a node, and we can start to null out or put less power on other nodes, i.e. interference mechanisms. So it's a very strong technique. This chart here just helps to drive home, again, that fact. What's kind of the interesting point to make is A beam steering antenna system on a client side is going to provide the improvement where we really need it, when you're in a very weak or a marginal signal strength environment. And as it turns out, just the way a cellular-based communication system is set up, that's what we wind up seeing. When you're in a very strong signal strength environment, you're already supporting a very high data rate. So if we drop in a beam steering system and provide additional antenna system gain, you may see some improvement, but it's not that much because you're already performing quite well. But when you're in a very weak signal strength environment, that's where a few dB of antenna system gain can really step in and provide a few to several dB of system level improvement. And that's what we're showing here by relating a CQI or an SNR value to a modulation scheme and then how it affects the spectral efficiency. So a couple of products have been developed, and one of them is where I'm at now, Taoglas. They have been developing a product called Shift. I'm just going to show just some basic data, again, to highlight that if you can get control of the radiation patterns on an LTE network on the client side of the device, you can pick up better system level performance. What Shift is, it is an LTE router inside of a single plastic housing, but 2x2 MIMO, but instead of having two passive antennas, there are two beam steering antennas. Each of these beam steering antennas has got 5 radiation patterns, 1 omni pattern, and then the other 4 take 360-degree azimuth and break it up into 4 sectors. So we're able to boost the gain by 3 to 5 dB on those 4 sectorized patterns. Obviously, we have to drop in an algorithm to interface baseband to command the antennas. But just to show a little bit of data, again, it works best in a weak signal strength environment. So this is downtown San Diego. This is 2 floors underground in a high-rise building. We found a very weak location where the same LTE router with external passive antennas could not pick up signals at multiple locations in the parking garage. We went back and compared it to Shift, again, the same radio LTE router with 2 beam steering antennas, and we saw that at 4 of the 6 locations, Shift was able to make a connection and support data throughput. The passive antennas were not able to. And then on the graph on the right, you can see up at outdoor street level, we went ahead and verified both systems are operational and did a comparison. But again, just highlighting in measured data and also conceptually, the point to make is a passive antenna in a cellular network is an inefficient process, but that's what we have and that's what works today. But for cellular, Wi-Fi, or other radio modulation schemes or protocols, if you can go from a passive to a beam steering antenna, there's a lot of benefit to be had. Another example, Wi-Fi beam steering antenna. This was work that was being done at another company back in 2013, 2015 timeframe, and they developed technology where you can go to a single antenna. And instead of having a single radiation pattern, think about a single 3D radiation pattern from that antenna. By implementing a 4-port switch, they could actually stay on frequency and generate 4 different radiation patterns. And these are all low to moderate directivity patterns, but think about peaks and nulls moving around as you go from mode 0, mode 1, mode 2, mode 3. And again, writing an algorithm and interfacing it with Wi-Fi baseband, a lot of test house data was taken comparing 802.11 AC 4x4 router with 4 passive antennas and then with 4 of these active antennas, each active antenna having 4 modes. A lot of test house data was taken. So what I'm showing here is a 3,100 square foot test house, 2 stories, locations were mapped out, an access point on the bottom floor, 4 test locations on the upper floors, and what we see is I'm mapping the RSSI at the different locations in the house. This example here is actually a 3x3. So there are 3 passive antennas on a Wi-Fi on the access point, and then the 3 passive antennas were replaced with 3 active steering antennas, each antenna with 4 radiation patterns. What I'm showing on the plot on the right is measured data. It is measured throughput data, megabit per second at the 5 gigahertz Wi-Fi band. It is at the different locations in the house. And it is for 3 different scenarios. The 3 passive antennas with adaptive beamforming, digital beamforming turned off or disabled in the AC router. And then with digital beamforming enabled is the blue curve. And then with digital beamforming enabled, but now with the active steering antennas, you see the red curve. And really, this is really what you should expect, because again, the 3 passive antennas on that Wi-Fi router are transmitting and receiving and providing coverage over in a multipath environment in, at different locations within a home. But if you can actually generate additional radiation patterns and accurately select correctly a better radiation mode, then you should be able to benefit. And that's actually what we saw in throughput testing. So again, this is an example of this is not a electrically large array. This was a small form factor antenna replacing a small form factor passive antenna that could generate additional radiation patterns, i.e. beam steer. And this is showing the benefits that could be had if you can implement that type of a technique.
Okay,
so again,
so
just
Jeff,
yeah, go ahead.
Yeah, this is Tom. Thank you. I was wondering if we could take a short question break now.
Yep.
It seems like maybe a good spot for that. I know you commented before when we spoke that you're okay to go longer.
Oh yeah, no problem.
Yeah.
Well, I'm stuck at home. I can't go anywhere, Tom. So what am I going to do, right?
Well, I hope all of our attendees. I'm on the edge of my seat really, because I think this data is really priceless to learn these things. And so thank you for this. So we have I'm trying to categorize questions, and I think there's maybe one it's a bit. It sounds like someone who is interested in sort of antenna manufacturing technology. We'll cover that one quickly, and then there's a couple on 5G, and then one on MIMO, and then so let me just get to it. So one of the questions is, what do you think about stamped metal antennas? They can be quite robust and have better efficiency perhaps than, according to the questionnaire, especially for small form factors.
They're very cost effective for high volume production. One of the limitations is that they found out in the smartphone years ago was it tends to be I guess you think of it as a 2.5D structure. I mean, you can stamp and bend it, but typically you don't have full 3D freedom for displaying a conductive element. So that's why typically you'll see LDS type antennas in smartphones, a 3D piece of molded plastic, and then there's metallization on that plastic. So now you've got a full 3D antenna that can curve and bend and flow in different along different faces. But no, stamped metal in a high volume application, it's very hard to beat that in terms of the economics, and it is efficient because it could be anywhere from a 5 to 8 mil thick, high conducting material.
Great. So I have a few questions I think about 5G and maybe related also to Wi-Fi 6 in a way, because with regard to MIMO order in a consumer device, I guess I personally, well, let me just ask the question. What is the limitation on orthogonality in a typical consumer device? Is 3x3 or even 4x4 believable? How can we get this high number of independent streams?
Well, I don't have the handset model number on the top of my head, and I was kind of anticipating this question, but with a little bit of research, I think you will find that in 2015 to 2017 timeframe, I think on the T-Mobile network at the higher LTE bands in their smartphones, on some of their smartphones, they had 4x4 LTE. There were 4 antennas that were servicing some of the higher LTE bands. The higher being, the bands falling in the 1.8, 2.1 gigahertz range. I know where it's a good question. In other words, if you're going to confine yourself to a smartphone, it's very hard to maintain isolation between the two antennas at the sub 1 gigahertz bands. And if you attempt to add more, in my opinion, the system collapses. You really can't do it because you're degrading the efficiency of all the antennas because they're coupling too much. At the higher frequencies, you're getting better performance off the main and secondary antenna in a smartphone. And at some of the higher LTE frequencies, you could add a third antenna and probably maintain acceptable isolation. Again, in a smartphone, the isolation requirements or specs are not as stringent as we find, like in the slide we're looking at here. This is a access point in your house where it's a larger volume device. You'll wind up with 15 to 20 dB isolation between the antennas. In fact, typically a solid 20 dB isolation between the antennas. In a smartphone, we're happy to get 10 dB at the lower sub 1 gigahertz, and then you might see 12 to 18 dB at the higher bands.
Okay, thank you. So there's a couple maybe 5G questions. I'll try to lump them together. One is 5G require, sort of circular polarization? There's a question about polarization. And then, we see, research papers where people talk about 10 and 20 dBi, but, what is that all about? Are there certain beam width and directivity requirements for future 5G applications? And I guess this is in the context of this sort of sub 8 gigahertz world, I think. So the questions are around 5G polarization, circular required, what are the beam width and directivity? And, people publish 20 dBi papers. What are those? I mean, what is that about? Is that even necessary?
Well, yeah, I mean, I'm pretty familiar with what's happening on the 5G sub 6 gigahertz node side. And typically what they're looking at now is a 32 to 64 element massive MIMO array for the node that would service the clients. But on that node, it's going to be it's dual linear components. It's not CP. I have not seen any CP requirement associated with 5G. If there is, I would like to see it and kind of see what they're talking about. Everything I see is typically linearly polarized antennas, and on the node side, it's like you see on a 4G base station, slant 45, two cross polarized, linearly polarized elements in a MIMO configuration is what's being proposed and actually implemented on the 5G sub 6 gig node side. On the client side, what we see or are anticipating is that higher order of MIMO. What used to be maybe 2 antennas, we anticipate to grow to 4 or 8 antennas. But again, those are linearly polarized.
Okay, thank you. I hopefully that helps address the question. And I guess for practical reasons, I apologize if folks would prefer a follow-up. But if folks want to ask a follow-up via the chat window, I'd be happy to try to pose it at the end. There's an interesting question here about you talked about feedback. Do you think AI will play a role in this sort of adaptive steering world? Artificial intelligence.
Yeah, I mean, at the end of the day, I'm an antenna guy, Tom. Probably that's a little above my pay grade, but I've worked at a couple of companies that implemented the cellular and the Wi-Fi beam steering that we're showing here in these slides. Typically, we brought on, algorithm developer, some software guys, a driver guy. So there's a little, you form a group, but at the end of the day, it's an algorithm. And I guess maybe what the person asking the question, can that be, how extensive and evolving can that algorithm get? And I'm possibly, but I mean, what we see is, we've seen this test data here shows that an algorithm driving a beam steering system in a multipath environment seems to work well. Could it work better with AI or higher levels of, or a more complex algorithm? Possibly, yeah.
One last question for this session here. This is very different, but I think it's you know, reflective of the range of interest that we have in this talk. And the question's about space missions, and I don't know if you have any, you know, awareness in that area, but I'm sure you do at some level. And, you know, like how do we get signals, you know, and from the space station, like level from Earth terrestrial, and then out to like Cassini, when it's going around Jupiter? I mean, that's really fascinating. And what are, just at a broad level, high level, like what's involved in those kind of antennas? Is there, do you know, or?
Well, yeah, and that, as it turns out, that's a different problem. And that's one reason why when I started this talk, I think it was important to say, hey, I'm talking about client devices where we're constrained to a small volumetric, you know, entity, smartphone, medical device. As soon as you start going to, I spent quite a bit of time in the aircraft industry, a little bit on space. There it's a different problem, but they have, the tools they have at hand is, instead of looking at these 2, 3, 5, 7 dBi, they'll actually put in a reflector, a high gain reflector, or they could put in a phased array. They'll drive up the much higher gain values on both ends of that link. So that's where you will see 20, 25, even 28 to 30 dBi of gain on one or both ends of a link when they're looking, say, from the space station to a some type of satellite that's quite far away. And again, it just goes back to, and there it's a bit simpler problem in the fact that you're not dealing in a multipath environment. So you're back to that Frisk transmission formula where you've got gain on one side of a link, gain on the other, and you know exactly where you want to point and transmit or receive to. So once you, so I guess that what makes, you know, it's a difficult problem. What makes it easy is it's not a cellular or Wi-Fi type problem where you're connecting multiple devices to nodes. It is a 2 ends of a link and 2 high gain antennas that are being pointed.
Great, thank you.
But that takes, and that's why we went back, we talked about Wheeler's formula, that takes volume. Those 20 dBi antenna is quite large, but they can do that on a, you know, on a satellite or a space station, those type of structures. You don't want to put one in your pocket. That's the problem.
Okay, very good. Thank you, Jeff. That's about it for this session, I think.
Yep. Well, I can wrap this up in about 5 minutes. There's just a couple of slides here that really take antenna theory and really bring it to the real world in a kind of an extreme case. These are actually, should be interesting. These are a couple of slides that we show to RF design and product design teams, kind of like say, when you develop a new product and you show us a concept, how do we decide, or how can we integrate different antennas into that product efficiently? And let's take an example. What we quite often see in an IoT device, a medical wearable device, a smartphone, or these different applications, there's going to be a cellular radio, could be a GPS receiver, Wi-Fi, or Bluetooth. So there's going to be multiple radios, multiple antennas. And what is our decision process? And it turns out, actually turns out to be pretty easy. And it goes back again to frequency of operation, bandwidth, and the size of the device. We position the cellular antenna first because that is typically going to have to occupy the lowest frequency and the widest bandwidth. So that gets priority. Typically, we'll position the GPS antenna second because though it is a narrowband function, we do want, you know, moderate to good efficiency to maintain good positioning accuracy. Wi-Fi or Bluetooth, it benefits from being a moderate to narrow bandwidth. It is at a higher frequency. It is a smaller antenna, so it can typically be positioned last. So that's kind of the 1, 2, 3 of how do we decide which antenna to place first and which one to position last. And here is an example of a device, a couple of radios. This has got cellular functionality and GPS receiver. So I'm just kind of pointing out that, you know, kind of that thought process is based upon what we saw in previous slides on that ground plane cut down test and Wheeler's formula. We'll position the cellular antenna so it has got a long extent of the ground plane of that device to operate off of. So that kind of dictates where the cellular antenna is going to go. GPS is not as position sensitive, but we do want to optimize separation. So we're going to place it on the other end of this small ground plane based device. If there is Bluetooth or Wi-Fi functionality, I kind of have a circle on the bottom showing where that could go. And typically that area is big enough for an antenna that would provide good performance at Bluetooth or Wi-Fi, because Bluetooth Wi-Fi is going to sit at 2.4 or the 5 gigahertz band. So that's kind of that thought process. And typically we will prototype even before, say, a customer has got a prototype radio system up and running for testing. We can actually generate a ground plane, place antennas at different locations, and start to map out, match the antennas, map out the efficiency we're getting over the frequency bandwidth. And what I'm showing here is a cellular LTE type configuration, main antenna on the top of the picture on the left, diversity antenna on the bottom left of the photo, and then the GPS antenna. And as you can see, the trade-offs are already happening, because the well-positioned LTE cellular antenna at the top, it has got a long ground plane extent to operate off of. On the bottom plot on the right, where I'm plotting efficiency at the low LTE bands, you can see the blue curve. The primary antenna, the main antenna, has got better efficiency. The diversity antenna does not have a long enough ground plane to efficiently operate off of at the lower frequency bands. That is why its efficiency is down 20%. Again, we know that ahead of time. So again, it goes into that proper antenna, understanding of the antenna, and then proper positioning of the antenna to at least maintain best performance on the main, and then maintain adequate performance on that diversity antenna. And the last thing I want to point out, the last two slides, and this is becoming more and more important. It's been important for years, but maybe to a lot of people it really wasn't. It is an overlooked parameter. We talk about efficiency, we talk about return loss, very important in antennas, isolation. And quite often we get an isolation spec, and that's good, but what we need to realize is with 5G coming on, or as we see on Wi-Fi, as they're going from 4x4, 8x8 to higher antenna count, as the antenna count goes up, there is a strong potential that the efficiency of our antennas are going to drop, because we're going to have finite isolation between all the antennas in the system. So the reduced isolation, if we can't maintain good enough isolation, we'll see a reduced efficiency, because instead of power being radiated out of antenna 1 in the figure, some of the power is being coupled into its neighboring antennas, and that gets fed back into transceiver ports. Reduced isolation in the MIMO system will directly result in lower data rates. And at the last slide here, what's important to point out is it's really it turns out it's a simple calculation, and it's like a bookkeeping task. If I've got a 4 antenna system, all 4 antennas operate at the same band. These could be 4 LTE antennas or 4 Wi-Fi antennas. Let's assume these are low band LTE antennas. I'm only able to get an 8 dB return loss, and I'm able to get 12 dB isolation between antenna 1 and 2, and then 16 dB isolation between antennas 1 and 3 and 1 and 4. I can very quickly calculate the mismatch loss based on my 8 dB return loss. I can calculate the amount of power that I'm going to lose due to this finite isolation. That is power that is coupled from antenna 1 to antennas 2, 3, and 4. And as it turns out, going through this bookkeeping type process, I can very quickly see what my maximum achievable efficiency is going to be. So if I can measure return loss on a prototype antenna and measure isolation, I can very quickly determine what the maximum efficiency will be from those just very basic network analyzer measurements. But the important point to make is 5G comes along and we integrate more antennas. Let's say there's going to be 4 cellular antennas in a client device, a GPS antenna, and it turns out to be 4x4 Wi-Fi antennas. There's 9 antennas. So you're going to wind up with an isolation matrix of antenna 1 coupling to 8 additional antennas in that system. And depending on the isolation you get, you go through this bookkeeping process, you're going to see the losses climb. So an important point to make is isolation is and will become more important as we make that transition from 4G to 5G. And that's all I've got. So.
Well, thank you very much, Jeff. That was really a great talk. I think, very accessible, and then also providing lots of experimental data. So there's just I think a couple more questions, you know, and you're getting some compliments. And, you know, one of the things, I have a kind of a question about the isolation point that you're making. And, you know, just a quick follow-up on the AI question, that one of the attendees was commenting that I think it's, you know, the comment is that they believe that AI is being used in some 5G calibration routines in MIMO systems. But, you know, when we all are having a challenge, I think, with how well can these MIMO systems work. So there's a few questions around the MIMO deal. And one of them is around isolation. So I feel I'd like to kind of sort of amplify that question with sort of my question, which is, it's conceivable, and it is in the literature, to have a multi-port matching network for, let's just say, a pair of antennas, where you, using a lossless network, cancel the coupling that exists out there, you know, at the antenna. And in fact, there was some research done, I think at the University of Utah years ago, on that has some relationship to guaranteeing orthogonality of the patterns. I was just wondering if that's something that is just kind of a intellectual curiosity, or if there could be some legs to that in your view.
Well, I mean, there are a lot of techniques have been or are currently being developed to improve isolation, some cancellation techniques like you kind of hit upon on that, say, isolation between adjacent antennas. The main issue is, and that's why I tried to, you know, kind of highlight the volume aspects of an antenna, that if the technique, there are techniques that can provide benefit, but can they be implemented in the volumetrics that were given for that client device? Something you're going to put in your pocket, or it's sitting on the water meter out in your front yard. So this all really, at least the focus of this talk was to say, hey, if I have to constrain myself to a fixed volume and put multiple antennas into it, there's a certain level of performance I can hit. But yeah, there are techniques out there, and as long as those techniques can be implemented and fit in the volume of, say, devices that we're looking at designing, then yeah, let's go for it. I think one of I forgot the name of the technique. It's been around a long time, and it kind of got revived again around 2008, 9, 10. But you take two antennas that are sitting side by side, you can actually take a small amount of power from antenna number 1, couple it back into antenna number 2, introduce 180-degree phase shift, and over a narrow to moderate band provide complete cancellation of that coupled component. So I mean, there are techniques out there, but then you just have to implement them. And I think you use the term lossless network. The problem is I can't find a lossless, you know, network. Everything has losses, but it is something you can manage.
Yeah, that's right. So
send me a link for that lossless component, Tom, and I'm going to buy some.
Yeah.
Okay.
So one last question maybe about the MIMO is kind of related. Is you know, do MIMO antennas on the client side in 5G steer according to nulls, or just toward, you know, direction of signal? And I think, you know, we talk about MIMO, which has a, you know, definite sort of like what it is. It's, you know, ideally orthogonal multiple, you know, streams. But we also know that, you know, in practice, and you're bringing it up, that you can beam steer. And I think the question is it more common to, you know, steer a null in 5G multi-antenna techniques, or is it more common to, you know, increase the gain in the direction that's advantageous?
Well, I mean, I don't have the, you know, a straight answer. I can add a little bit to that, though. When I was showing the data on that test house, we were doing a lot of work at Wi-Fi 802.11 AC, and 4x4 antenna systems on a access point. And what surprised us was working with the rest of the industry, the radio chipset and the baseband people. The thing that surprised us the most was I was walking in 2013-14 timeframe thinking a 4x4 antenna system was operating in MIMO mode most of the time. And as it turned out, we were told no, most of the time for that access point sitting in your home, it's doing adaptive beam steering because they were getting better connectivity, higher SINR or higher SNR by forming in the digital domain a 4-element array instead of trying to drive that as a MIMO. In very close to device, it might be in MIMO, but typically we were told 90% of the time it's in adaptive beamforming mode. So that type of information might, you can start to speculate on 5G on a client-side device. As we introduce 4 or 8 antennas in a device, how often is it going to be driven as a MIMO system, and how often is it going to be using adaptive beamforming to form effectively a 4 or 8 element array? And if you form that 4 or 8 element array, you can go back and you can decide what do you want to null out and interfere and apply power on target, or do you want to or are you just concerned about optimizing radiated power back at that node? I mean, I would think interference, nulling is going to be pretty prevalent, but I can't, that's more of the protocol and the algorithm guys. But I would think they'll be implementing nulling to null out, because as it turns out, and again, we were told many years ago on cellular networks, weak signals are not the problem, it's interference. So when you start talking about SINR, it's not the S you're worried about. You need to worry about the I, the interference, and techniques that can mitigate interference in a cellular network are very good.
So there's one last question, which and then we'll let you go. I think the questioner is thinking about maybe the higher frequency stuff in 5G. I'm not really sure if we're thinking, the cellular and unlicensed, which could be up in the 7 gigahertz band, but then also maybe this is more geared toward the short range of millimeter wave. So I know you're working in millimeter wave, and this talk has been restricted to sub 8 gigahertz. But the question is the questioner is saying, what's the good solution for the high frequency 5G stuff? And it's maybe that's a subject for a future talk, but maybe a quick answer to that, and then I think we'll let you go. So.
Well, yeah, I mean, what's happening? Yeah, I'm spending all my time now or most of my time on millimeter wave system development for client devices and nodes. 28 gigahertz band is quite popular now. But if you look at it, you can buy smartphones now in the U.S., a limited number that have got the Qualcomm chipset, and there are, I think, 3 4-element arrays in that smartphone. Operating, 28 gigahertz. So I would assume that'd be for the Verizon network, because they've been pretty prevalent in rolling out systems in a lot of the urban centers in U.S. cities. So really, I mean, for millimeter wave, the way I think they're going to run on a client device, say the smartphone, it's going to be 4-element arrays. So they're going to have a certain, EIRP. It's not going to be very robust, but back on the node, they're looking at, 64, 128, 256 elements. So they can drive the gain up on the node, up to that 22 to 28 or 22 to 30 dBi gain level. So you can get a very high gain on the node in a very small area because of the small size of the antennas to support a high EIRP. On the client side, you cannot go with a single antenna. They need to form some type of an array to get the antenna gain up. So what I see in smartphones right now is a linear 4-element array. They'll drop, say, 3 of them in to provide, somewhat robust coverage around that smartphone. Because again, you cannot you don't know the orientation of the smartphone, and it is mobile, and its position is always changing. So you have to kind of always be ready to, you know, anticipate the need to form a connection in different aspect angles associated with that smartphone.
What kind of gain can you get out of a 4-element array at 28 gigahertz?
Not much. How's that? That's the short. Oh, you want a number? I knew back in 2017, going to some conferences, they were talking. They would like at least 8.5 dBi of antenna gain on the smartphone. 4-element. Let's say if you could maintain 5 dBi out of a patch, you're looking at 3 dB when you combine 2, another 3 when you go from 2 to 4, 11. But you know, you've got losses at those frequencies. So I think the 4-element array, they may be able to get somewhere between 8.5 and 10 dBi.
Excellent. Thank you very much, Jeff. All right. Well, thank you everyone for attending, and thank you so much, Jeff, for this excellent talk. Many people have really thanked you for the talk, and yeah, thanks again.
Okay. Well, thank you, and I really enjoyed it, and I appreciate the opportunity to present.
Yep, let's share. Thanks again very much, Jeff. So in closing, I just I hope you guys can see my screen here. Just wanted to encourage everybody who's not a member to become an IEEE member. And if you're not an MTT member, consider becoming an MTT member. And of course, for future events, if you're on LinkedIn, follow the hashtag MTT-SCV. And we will be coming up with a schedule for future events for the rest of the year. So with that, I would like to close out the proceedings. Thanks to everybody who attended. It was one of our best attended talks so far. So thanks, Jeff, and thanks everybody for attending. And we see you next time.
Thanks, Akash.